Hello students, welcome back to today's class on real numbers, and this is the lecture number 2 in the same context of what we are discussing in the previous class, right? My name is Avinash and I'm a graduate from IIT Kharagpur. Let's start today's session. So in the previous class, when we are discussing about real numbers, we are discussing what are decimal numbers and how to represent, or what are the types of decimal numbers, right? We have discussed terminating and non-terminating. Terminating means there is a stop for that. Non-terminating are the numbers which don't have any stop. They're just continuing in that flow forever. Okay, so we have terminating and non-terminating. Every rational number can be expressed as a terminating decimal or a non-terminating recurring decimal. Every rational number can be expressed either in terminating or non-terminating. Recurring means repeating. Recurring means repeating. Okay, so we'll try to discuss. We discussed already what are terminating. Okay, a decimal number is said to be terminating decimal if the decimal number contains a finite number of digits. Finite number, it can be 1, it can be 10, it can be 100, but the digits are finite. Okay, in the same way, we have some examples for terminating, and this is an example 0.5666 and so on, which is non-terminating, which is not terminating. Okay, and we can see the non-terminating which continues endlessly. Which continues endlessly. You can see 0.5666 and so on. So some pattern is there or no pattern, but it is just repeating. It is just continuing its endless journey. We say them as non-terminating. There is no stop for that. Non-terminating means there is no stop for that. Okay, the same way, we have other kind of decimal numbers where we say recurring and non-recurring. Recurring means repeating. Recurring means repeating. Okay, so what are the types? A recurring decimal is a decimal number in which a group of figures is repeated infinitely. Is repeated, you can see here 0.54848484848 is just continuing its journey. Right, it is repeating. 0.48 is repeating. Recurring decimals can also be called as repeating decimals, right? And which does not have any other pattern, no group of digits repeating endlessly. We say they are non-recurring or non-repeating. You can see here 5, 4, 8, 4, 5, 7, 9, 8. There is no pattern, right? So all these things which we have discussed in the previous classes, and we discussed a couple of examples also. Let's continue our discussion with all these numbers. Okay, the first one here we are going to discuss in today's class is expressing a 1.62 bar. What do you mean by bar? It is 1.626262 and so on. There is no end for that. It is recurring in the form of p by q, where q is not equal to 0, p and q are integers. Simply express this 1.62 as a rational number. What is the meaning of this one? 1.62626262. How many digits in that way? There is no end. When bar is there, there is no end. It just continues in that way endlessly. Okay, now if this is the pattern it's following, let x is equal to 0.62. We have two numbers which are repeating, so I'm taking x is equal to 0.62. We'll try to bring some relations between all this. So as I have 0.62, two values which are being repeated continuously, recurring continuously, I'll multiply with 100. Why 100? Because I want to eliminate these two zeros. Okay, it's actually 0.626262 and so on. Okay, 0.62 bar actually. Okay, so 0.62 bar. So what I do, I'll multiply with 100. So 100x is equal to 0.626262 so on. So we can say that when you are multiplying with 100, this decimal will be shifted to 2 places later. So that will give you 62.626262 and so on. How can you write this one? 100x is equal to 62 plus 100x is equal to 62 plus, okay, 0.62 and so on, correct? Simply this 100x is equal to 62 plus this 0.62 is nothing but x. is nothing but x, correct? Okay, so 100x and bring this x here, 100x minus x. 100x minus x is equal to 62. So that will give you 99x is equal to 62. So you can see that x is equal to 62 by 99. This is 62 by 99. That is the value of 62 bar, but we still have 1. See, the question given is 1.62 bar, right? Which is equal to 1 plus 0.62 bar. 1 plus 0.62 bar, we got it as 62 by 99. 0.62 bar, we got it as 62 by 99. So you need to do this one, okay? 1.62 bar. So 99 plus 62. 99 plus 62 by 99. So tell me, what is 99 plus 62? It is 161 by 99. 62 and 99, 11 and 16, 161 by 99. So P by Q form of 1.62 bar, 1.62 bar, we can write as 161 by 99. 161 by 99. Okay, you can carefully see here. X is equal to 0.62. Don't leave your answer with this one, because that is the value of 0.62 bar, not 1.62 bar. Sometimes it may ask with 2.62 bar. Sometimes it may be asked for 3 point. Based on that, you need to change and you need to add them, right? So let's move forward for the next question. So this is how you can try to convert this recurring decimal number into P by Q form, which is considered as a rational number. You can see 161 by 99 is a rational number, right? Let's move forward to see more numbers. Express 1.23 bar in the form of P by Q. Same type of question. Let me solve that once again. So as we have 2 digits, let x is equal to 0.23. 0.23 bar. So as we are having 2 digits, let me multiply with 100. 100x is equal to 23.232323 and so on. 100x is equal to 23.232323 and so on. So now what I will do, we already have 0.23. Okay, see, in the previous case what we had done, if you can remember, okay, this 0.62 we have written it again as x. The same way, now it is a 0.23, right? So 100x is equal to 23 plus 0.23 bar. 23 plus 0.23 bar. 0.23 bar is again equal to x. Okay, so 100x is equal to 23 plus x. If you transfer this x here, 100x minus x. 100x minus x is equal to 23. 100 minus 1, 99x is equal to 23. And x is equal to 23 by 99. X is equal to 23 by 99, right? So x is equal to 23 by 99, which is equal to 0.23 bar. 0.23 bar is equal to 23 by 99. That's okay. But what about this one? 1.23 bar. We need to write for 1.23 bar, which is 1 plus 23 by 99. 1 plus 23 by 99. So if you add these two, if you take LCM, 99 plus 23, which will give you 122 by 99. Which will give you 122 by 99. Clear? Okay, so this is how you can convert the recurring decimal number to a P by Q form of rational number. Correct? Let's move for the next question. Okay, so we have few questions here. We need to do that. A number which is rational but is not an integer. A number which is a rational but not an integer. We have a lot of numbers. 1 by 2. This is a rational number but not an integer, right? 1 by 3, 1 by 4, 1 by 5, 1 by 6. Any P by Q format which you cannot finally convert that into integer is always a rational but not an integer. A whole number which is not a natural number. You know that. Very easy. Whole number starts from 0, 1, 2, 3. Whole number starts from 0, 1, 2, 3, so on. Which is not a natural number. Natural number starts with 1, 2, 3, so on. So 0 will be there here. 0. Okay. Whole number which is not a natural number. That is the answer, 0. Let's move forward. A number which is a natural number, whole number, integer and a rational number. every natural number, let's say 1, which is a natural, which is a whole number, which is an integer, which is a rational number. You take any natural number, it will correct. Okay, 1, 2, 3, 4. Simply you can take natural numbers as the answer for that. So the next question, a number which is an integer but not a natural number. You can take any negative numbers, which is an integer -2 but not a natural number. -1, -3, -4, all these numbers are integers but not natural number, even 0, but not positive numbers. The positive numbers again will go for natural numbers, right? So let's move forward to see the next one. Insert 3 rational numbers between 3/5 and 2/3. So here I'll give you 2 methods. Okay, one using LCM equating the denominators, other using mean method, which we have discussed earlier. Okay, the first one, making the denominators equal 3/5 and 2/3. So now tell me, what is LCM of 5 and 3? LCM of 5 and 3 is 15. LCM of 5 and 3 is equal to 15. Both are prime numbers. Just multiply them. Okay. So what you do, you as you have 3/5, multiply with into 2 into 3/3, and here multiply with 5/5, or simply take LCMs. I mean to say equate the bases, denominators. 3 into 3 is 9, 9/15, and 5 2 is 10, 10/15. Okay, is it correct? 3/5 and 2/3. Now what we are doing, into 5 we have done, into 3 we have done 9/15, into 5 we have done 10/15. But still we want to write 3 numbers between them. Although it's not that easy. Okay, we'll try to write this 9/15 as 90/150, and this is as 100/150. So in between them we can easily write lot of numbers. So your answers can be 91/150, your answer can be 92/150, 93/140, so on, 99/150. So all these numbers are rational numbers in between 3/5 and 2/3. Or we also discussed mean method. We remember mean method, if you have two numbers a and b, a number in between them can be taken as a plus b/2. A number in between them can be taken as a plus b/2. So what we can do, we have 3/5, we have 3/5 and 2/3. So a plus b/2, you can take it as 3/5 plus 2/3/2. You try to find this value, that is one number. Insert 3, again in between these two, use the same formula again to get one more. Using these two, use the same formula to get one more. That's not that easy as we have done like this. So the base thing is, you always try to equate the bases or the denominators. The rest everything will be very easy. Correct? Next one. Express the rational number 242/1000 in decimal form. See, whenever you have 1000 or 100, 10 or 10,000, 1 lakh, very easy. I'll give you small things. For example, I have 2/10. Okay, 2/10. We have 1 0 here. So that means we need to keep one decimal place in the final answer. 0.2. You can divide it normally, you'll understand. Okay, 10 and 2, you keep 0.0, 10 2s are 20. So similar, the same number will come here with one decimal. If I go for 21/100, now we need to go for 2 decimal places because we have 2 zeros in the end, in the denominator. So that will give you 0.21. After decimal, you should have 2 values. Yes, you are having. Right? In the same way, 242/1000, here you have 3 zeros. So you need to keep 3 values, 3 decimals before. So okay, so this is first place, second place, and third place. So here is the point. So 242/1000 can simply be written as 0.242. If you're not clear, divide. If you're not clear, 1000 and 242. Okay, so 0 point, keep a point and keep a 0 because 242 is less than 1000. 1002 is 2000. Then we are having 420. Right? So then what we do? Final answer is 2.242. Okay, so keep one more 0 and keep 4. So 1000 into 4 is 4000. You will get 200. Keep one more 0. Keep one more 0. 1000 twos are 2000. 1000 twos are 2000. So that is done it. 0.242. No need to do all this division always. Whenever you have by 1000, as many number of zeros are there, you just try to replace your decimal point into that many places. 2 zeros, so 1 and 2 always come from the left, from the right, okay, right to left. So that becomes 24.20, 24.20. Right. Okay, so let's move forward for the next one. Express the rational number 22 by 7 in decimal form. The normal division, nothing else. So let's try to divide. 7 and 22, so we'll get 7 3s are 21. 7 3s are 21, so we'll get 1 here. And 0.0. 7 1s are 7 again, you're left with 3. Once again, you can try to bring 0. Once you replaced decimal, once you kept point, you can bring any number of zeros you want, depending on the requirement. Okay, so 7 4s are 28. Once again, you're left with 2, 0, 7 2s, 14, 6, and it continues like that. 3.142. Okay, it goes on continuing that. Generally, 22 by 7, we take it as approximately equal to 3.14, and this is what we say pi. This is what we say pi, that is used in circles. Area of circle pi r square, perimeter of circle 2 pi r, the same pi, okay. Right, so let's move forward for the next one. Express the rational number 354 by 500 in decimal form. 354 by 500. So I'll give you a very easy method. As we are having 500, instead of dividing with 500, let's try to eliminate that. Eliminate in the sense, try to make it as 1000. Try to make it as 1000, that means into 2 by 2. So 354 into 4 2s are 8, 5 2s are 10, 3 2s are 6, 7. So that becomes 708, 708 by 500 into 2 by 1000, 708 by 1000. So these 3 zeros will be shifted towards 3 decimal places. So that will give you 0.708. That will give you 0.708. Done. All right. So let's move forward for the next question. Express 15 by 15.4 in the form of P by Q, where P and Q are integers. Just how we told you, in decimals, as many points you're having, that many number of zeros will come. As many decimal values are there towards the right of point. So as we have 1 point, we can write it as 154 by 10. You can leave it like this, or you can just try to divide with 2. So 2 7s 14, 2 7s again 77 by 5. 77 by 5 is the answer, or 154 by 10, both are same. Okay, so this is how you can represent a decimal number to a rational number. Moving ahead, express 0.36 in the form of P by Q. 0.36, you can carefully see here, you're having after point, you have two values. So if you want to eliminate that decimal, divide with as many number of zeros. That means 0.36 has 2. So I'll multiply with 100 and divide with 100. As it is having 2 values, so into 100 by 100. So that will give you 36.36 into 100. 36 by 100. 36 by 100. So you can simply solve that more. With 4 9s are 36 and 4 25s. So 9 by 25 is the answer, or you can also leave it as 36 by 100. You can also leave it as a 36 by 100, right? So let's move forward for the next one. Express 10.25 in the form of P by Q. 10.25, as you have 2 decimals, 1025 by 100. 2 values, 2 zeros. You can leave like this, or you can try to find. So 25, I think we can cancel 25. 25 4s. What about this one? 25 into 40 is 1000. 25 1025. 25 4s 100. Well, with 2, right? And then we can bring 5. 25 1s are 25. So 25 into 41. With 25 we cancel, we got 41 and this 4, 41 by 4. Right? So this is how you can try to change or convert decimal numbers to rational numbers. Decimal numbers to rational numbers. Okay. So let's move forward to the next one. Every terminating decimal number has a denominator in the form of 2 power m into 5 power n. Terminating means it should stop. The decimal values should stop. So what is the pattern, or how to identify whether a number is terminating or not? It should be able to express as 2 power m 5 power n. If we can express the denominator in that form, we can say that it is a terminating, or else it is not terminating. Let me take some examples. 22 by 200, 485 by 500, 22 by 10. Carefully see. In the denominators, these are the multiples of 2 and 5. Correct? Or multiples of 10, you can say clearly. 200 is actually equal to 2 into 100, 2 into 10 into 10, 2 into 10 into 10, 2 into 2 into 5, and this 10 is again 2 into 5. So 1, 2, 3, 2 cube. 5 into 5 is a 5 square. So 200 can be written in terms of 2 cube into 5 square. If you can write like this, these are terminating numbers. Okay, you can carefully check that. 222. So 0.0. 200 ones, 200, and we are left with again 20. So bring one more 0. 200 ones are 200. So it got terminated with the value of 0.11. 0.1. In the same way, 22 by 10 is 2.2. Same way you can try to find what is the value. It may be 997 or 970, something like that. Right? By 500, so 9 point something. Sorry, 0.97, something like that. Okay, you just please try to verify that. So this is how terminating numbers will be there. But what about non-terminating numbers? What about non-terminating numbers? If the denominator is not in the form of 2 power m 5 power n, then the decimal is non-terminating. If the denominator is not in this form, we can say that it is non-terminating. Right. So let's move forward. Express 0.36 bar, which you have already done. I'm not doing that again. I'm just giving you as a work. 0.36. You can write this as 0.36 bar. So let us take x is equal to 0.36 bar. 0.36 bar. So 100x is equal to 36 point again 36 bar. 2 decimals. What is the meaning of this one? It is 0.36, 36, 36 and so on. 0.36, 36, 36 and so on. Right? So that is how you follow. We have already done this. So using the same example, you can try to understand what about this. Okay. So the next one we're going to discuss in the next class is all about irrational numbers. Till now what we have discussed are rational numbers, whether they are terminating or non-terminating, whatever it is, we don't care, but we have discussed about rational numbers. Now in the next class we are going to discuss about irrational numbers, right? So I hope you understood. Thank you so much, friends. Stay tuned to get the next lecture. Thank you.
Hello everyone. So today we'll be discussing about Newton's first law of motion. In total, there are Newton's 3 laws. Okay, Newton's first law, Newton's second law, and Newton's third law. So there are 3 laws, and all of them are laws of motion. They will be relating force and motion. We will be learning about them one by one gradually. Okay, so my name is Shashin Reddy. I'm a graduate from IIT Dhanbad. Let's go into the class. Okay, so to understand the history, okay, how it began and all, it began with a scientist called Galileo. And Galileo was before Newton. So Galileo has developed something. He discovered a few things. And that Newton continued. Okay, so let's go into the Galileo's experiment, the Galileo's activity. It's a very simple one. All of us can try it at our home. Okay, so look at the left animation, everyone. Both of them are similar. We'll go into the left animation first. Look at this one. Here you can clearly see there are 2 slopes. You can clearly see that there are 2 slopes and the ball is being released from here. Now what we can notice is if the ball is released from here, it will go to the same height, exactly the same height. Okay, will go exactly to the same height, and this slope will take it a very smooth surface. Will take what? Will take a smooth surface. If you take a rough surface, it will go to a lesser height. Okay, that is because of friction. So we'll take a smooth surface where friction is very less, and we'll notice that the ball will go exactly to the same height. And if you look at the second animation, it is the same. But the ball is released from the other end. The ball is released from here. It will again go to what? It will again go to the same height. So you can clearly see here and here the slopes are different. I mean the slopes in the journey of the ball. So here it is starting from what? The smaller slope and then going on the longer slope. But here it is starting from the longer slope and going into the smaller slope. The thing is, in both the cases, the ball will reach to the same height, exactly the same height. Alright, so Galileo has done this with different slopes. As you can see, there are 4 cases here. Right, look at the first case. In the first case, the ball is released from here. Now again, there are 2 inclined slopes. One slope and the second slope. So the ball will go on to the second slope until where? Until exactly the same height. See? Until the same height. And we are taking what? We are taking a very smooth surface. If it is rough, it will go, might be somewhere until here. A little lesser height, a little lower height. Okay? But in all the cases, when we take a smooth surface, we will notice that the ball will reach almost the same height. It could be in the second case, it could be in the third case. In first, second and third, the same thing happens. Okay, now Galileo started thinking. That is, let's say, I'll start taking it this way. Okay, if I leave the ball here, the ball is going exactly to the same height. Okay, first case. Then second case, the left side I'll keep it the same. The right side I'll increase the slope. That means if the ball is here, again it will go to the same height, it will go until here. So even if the distance of the journey is increasing, even if the distance of the second slope is increasing, it doesn't matter. It will still go to the same height. I can take another one also. Much longer one. But we'll still notice that the ball will go until what? Until the same height. So Galileo started wondering, how much ever longer slope I take, how much ever inclined it is, it doesn't matter, the ball is going to the same height. Then what if I take it in this way? See, understand this. What is the target of the ball? The target of the ball is to reach the same height. Yes or no? We notice that for every inclined plane. Okay. So its target is to reach the same height. So now, if I keep a horizontal plane here, then what happens? Then what happens to the ball? According to this, until it reaches the same height, it will keep on going. If its target is to reach the same height, the ball will keep on rolling until when? Until it reaches the same height. But if it is a horizontal surface, here, then the ball will come till here. Okay, then after that it will keep on going. It is completely horizontal. It will keep on going until it will reach the same height, and it will never reach the same height. It will go on until infinity, very, very far away. Okay, now you might think, sir, practically that doesn't happen. Why? Practically there is friction. Friction stops it. That is the reason why. But if you remove friction out of the picture, imagine that we take a surface where there is no friction. Practically not possible. That is the reason why I am saying imagine. So imagine for a moment that there is no friction here. Then what happens? Will the ball stop? No. The ball will keep on going. The ball will keep on going. Okay, and let's say Here its speed is, well, just take an example, 2 meter per second. Now I told you there is no friction, no one stopping it. It's a horizontal surface. Then what happens? Here also its speed will be 2 meter per second. See, if there is anyone pushing it, the speed will increase. There is no one pushing it from behind, no force pushing it from behind, so speed will not increase. There is no friction. Friction will decrease the speed normally. But here there is no friction. So speed also will not decrease. So no one is increasing the speed, no one is decreasing the speed. That means speed remains constant. That means speed remains constant. Is that clear? So Galileo wondered, from all these experiments, Galileo wondered that the natural state, he decided the natural state. What does natural state mean? By itself. Natural state of an object. So when we say natural state of an object, it means without any disturbance. Like, what is my natural state? When there is no one around me, how I behave is my natural behavior, natural state. When there is no one around me, when I am alone, my behavior is my natural behavior. Yes or no? Similarly, here when we say natural state of an object, it means the state of an object when there is no force acting on it. When there is no force acting on the object. When there is no force acting on the object. And see, here we'll again come back to our example on the horizontal surface. We discussed no one is pushing it from behind, no one is stopping it, so there is no force acting on it, and then what's happening? That is the natural state of the object. And here see, what is the natural state of the object? It is to maintain constant speed and in the same direction, so constant velocity. So the natural state of an object is to remain in the same state of motion. That means the same speed and the same direction. Both of them are equal. That means constant velocity. Okay, so if we discuss about this natural state of an object in more detail, now I am saying what I am saying, the force is equal to 0. Told you right? Natural state of an object is a state when there is no force acting on it. No one is influencing the object. No one else around me, right? Natural state of me, natural behavior of me. When there is no one around me, that is my natural behavior. Yes, similarly, when there is no force acting on an object, that will be the natural state of an object. And what is the natural state? It is of, natural state is of constant motion or constant velocity. And what is constant velocity? It is of uniform motion. You know that in uniform motion what happens? Velocity will remain constant. Velocity is constant. Understood everyone? So that's what Galileo concluded. Force is equal to 0. The natural state of an object is of what? Is of uniform motion. Now this is for any object. A very small object to a very big object, even the sun or earth. When there is no force acting on them, they will be in uniform motion. Now, here uniform motion in the sense velocity is constant. So if an object at rest, what will happen to object at rest? If there is no force acting on it, the object at rest will remain at rest. It will not move, right? So no force will mean an object at rest will remain at rest or will continue to be at rest. And an object in motion will be in the same state of motion. That means when I say same state of motion, its velocity will be constant. Its speed and the direction of motion will be constant. Is that clear? So these are the points Galileo concluded, and these are some brilliant points. Now Newton combined all of them and he gave Newton's first law. Newton combined all these points and he gave the first law of motion, And to honor Newton, we call it as Newton's first law of motion. Okay, we'll go into that, but these are the Galileo's experiment. We discussed all these points. You can go through them later on. Okay, we discussed all these points. Don't worry. So Newton's first law of motion. So what does it tell? Newton's first law of motion states that an object at rest will remain in the state of rest. Good. And an object in motion will continue to be in the same state of uniform motion. That is the natural state. Same state of uniform motion. And what does uniform motion mean? It will mean constant speed and along the same direction. It's the same direction in the sense along the same straight line. But there is a condition. When is this possible? Not always. That is possible for this condition. So it is important. Until and unless an external force is applied. That is the condition. Until and unless an external force is applied. So remember everyone, very simple point. Very simple point. In simple terms, what it says is, if force is 0, the object's velocity does not change. Simple. If force acting on an object is 0, or per se net force acting on an object is 0, if the speed of body initially is 30 meter per second, finally also it will be 30 meter per second because net force is 0. So speed does not change. Simple. So an object at rest will be in the same state of rest, and an object in motion will continue to be in the same state of uniform motion. If you say uniform motion, you are taking care of everything else. The condition is until and unless an external force is applied. Good? Simple? Okay. Now, from this, we will not get, any value for force. We do not get any formula for force, but we'll just get an understanding. What is the understanding? Force is something that changes the motion. Force is something that changes the state of motion. No force, no change in state of motion. So if there is force, the state of motion will change. So we are understanding what force is. Yes or no? That is the reason why we say it describes the qualitative effect. Only quality. Upar se. We can only discuss in words. Do we have a formula for how much force it will be? How much change it will make? No. So we only get a qualitative understanding of what? Of force. Clear? So that's what Newton's first law does or states. Simple. And everyone, it is important to understand each and every point in this. There are 3 main points. So please understand it and also practice it. Okay, good. Let's go into a few more cases. So a simple question for us. Can the state of motion of an object change without any force being exerted on it? What do you mean by exerted? Exerted will mean applied. So if there is no force applied on the object, will the state of motion change? Yes or no? What do you think? Yes or no? Yeah? And the answer is no. For motion to change, for the state of motion to change, there should be a force. Good? Wonderful. Let's go. That is the essence of Newton's first law. Right? Now again another interesting question. What is the natural tendency of an object? The natural state of an object. To continue in the same state of motion. To change the direction of motion. To change the speed of motion. To change the state of motion. A, B, C and D. What is the natural tendency of an object? Yeah, everyone, what is that going to be? Yeah? The correct answer is? The correct answer is option A, to continue to be or to continue in the same state of motion. We told you, right? We discussed this. What does natural tendency of an object mean? The tendency of an object when force is 0. And if force is 0, the state of motion does not change. It remains the same. So to continue in the same state of motion. Simple? Okay. Next. So now we'll discuss about inertia. Now inertia is just a name. A name for what? A name for a character. A name for a property. Which property? I'll explain. So let's go into a few examples first. What does lazy mean? Lazy means that person will not do any work. He'll just be sitting idly. He'll just be sitting there. Yes or no? So if there is a person who is just sitting there and not doing any work, he or she will be called lazy. Right? So that characteristic is called lazy. So we give it a name. Anyone just sitting like that, not doing any work, we call them as lazy. Simple. Right? Now, then we'll say, let's say, active person. What does active mean? A person, if there is a person who is willing to do any work, who is ready to do any work, we say that he is or he or she is active. So for every property, for every type of behavior, we are giving a name. The one who is not doing anything, we call him lazy. The one who is doing everything, he or she, we call him active. Yes or no? Now look at the object. Forget about persons, we'll look at objects. Now objects also have one property. What is that property? Now what is the natural state of an object? What is the natural state of an object? To remain in the same state of motion. That is a natural state. So we give it a name and we call it inertia. That's it. So all objects will resist a change in their state of motion. Yes or no? They are not, it's not even changing. When force is zero, the state of motion does not change. State of motion does not change. So that means every object, any object, will not allow the state of motion to change when force is zero. So by themselves, if you take an object, keep it there, not exerting any force, that object will say, whatever you do, I will not change my state of motion. Yes or no? If you just keep an object this way and you're not applying any force on the object, what will the object say? Whatever you want you do, I will not change my state of motion. Yes or no? Right? That's what object says. That is the characteristic of an object. Property of an object. Behavior of an object. And that behavior, we call it a name. We give it a name, inertia. Okay? So inertia is a natural tendency of an object to resist a change in its state of motion or of rest. So that is inertia, which is very important, everyone. Very, very important point, because inertia is nothing but the natural tendency of an object. To do what? To remain in the same state of motion. For it to be in the same state of motion, it will resist or oppose any change in its state of motion. Okay? And the mass of an object is a measure of its inertia. It's an important point, but we'll go back to it. We'll understand inertia in a few steps, and then we'll again go back to this point. You need not worry. I've just mentioned it here because it is important. And that is why the first law of motion. The first law of motion is nothing but natural tendency of object. So the first law of motion is also known as what? Also known as law of inertia. Because the first law of motion speaks about the natural tendency of an object. Okay, so let's try to understand inertia in much more detail. So first of all, inertia, there are two types of inertias. One is the static inertia. Now static will always mean at rest. So inertia of rest or inertia of an object at rest is called static inertia. And dynamic will mean change. So motion is changing or there is speed. Right? So inertia of motion is what? Dynamic inertia. So an object at rest, static inertia. Object in motion, dynamic inertia. We'll go into each and every one of them. Okay. So let's start with static inertia. Now have you any time experienced this? You're standing in a bus. Okay, you can take any vehicle for that matter. You can be sitting also. You can be sitting also, doesn't matter. Okay, so when the bus suddenly accelerates, what happens? Or think about this, you are sitting in a bike. Okay, your father or anyone else is driving the bike and you're sitting behind. And the driver, your father, let's say your father is sitting there, your father is driving the bike and you're sitting behind, and your father suddenly accelerates. Your father suddenly accelerates. What happens? You'll fall back. You'll go back, yes or no? Happens when there is sudden acceleration, you go back, you fall back. Every one of you would have experienced this on a bike or in a car or in a bus or any vehicle for that matter. Yes or no? Now why does that happen? Why? That we'll understand using what? Using inertia. Okay, so these are some good examples. I'll go into every one of them. So static inertia is a tendency of an object at rest to continue to be in the state of rest unless it is acted upon by an external force. Now what does this tell? We'll try to understand that using this example. Here, according to this, the person is standing in a bus and the bus is moving towards left. Or better, bus accelerates to left. Or I'll say bus starts moving towards left. Starts moving to left. Okay. So whenever you get these type of examples, I mean, you standing in a bus, sudden acceleration, sudden application of brakes, whatever it is, you have to divide the human body into two parts. One is the upper body, upper part, and the other is what? The lower part. Upper part and the lower part. Okay. Now you start imagining, everyone, okay? I'll explain, but start imagining things. This is the floor of the bus. So here, when we talk about inertia, you have to think about two cases. The initial case and the final case. So initially, the initial case. Initially, the bus is at rest and obviously I am standing in a bus. If the bus is not moving, I am also not moving. So the person and the bus are at rest. So if an object is at rest, which inertia it will have? Static inertia. An object at rest will have inertia of rest or static inertia. So this object possesses static inertia. Okay, now, final case. Bus accelerates all of a sudden. When we say accelerates, or you can say bus starts moving. You can say accelerates or starts moving all of a sudden. Then see what happens. Then what happens is, let's say the bus moves towards left. Your lower part, your legs, when I say lower part, they are the legs. Your legs are in contact with what? Contact with the floor of the bus. So, the floor of the bus is going towards left. So, your lower part will go along with it. Your lower part will go along with it, but our upper part, this is the upper part, above your legs, upper part. That upper part, initially it was at rest. Then finally also it will want to be at rest. Why? Because of inertia of rest. I told you, right? Inertia of rest is a property of an object at rest. And what does that property mean? It means it will try to be at rest. It will try to be at rest, so the upper part will be at rest. Well, matlab your upper part is there itself, but your legs are going forward. Then imagine what's happened. Like someone is pulling your leg forwards. What happens? You fall back. Because actually your legs are going forward, so your body goes back. Your upper body goes back because your legs go forward. What happens then? You fall back. That's what happens. Clear? So anytime you get these type of cases, trust me, initial case, final case, top of inertia, you will get the answer. So bus accelerates or starts moving all of a sudden. Lower part moves forward along with the bus. Moves forward along with the bus. But the upper part that we were talking about, the upper part, what will happen to the upper part? Upper part will remain in rest, will remain at rest due to what? You have to mention this, everyone. It's a very important point that you have to mention. Will remain at rest due to inertia of rest. So sir, which inertia, how do we identify? Simple, look at the initial case. Initially both of them are at rest. So if they are at rest, which property they will have? Which inertia they will have? They will have inertia of rest. That's it. This is the complete explanation. So if you write in this way, it will be very good. Everyone will understand that and it will be a beautiful answer. Okay? Understood everyone? So that's what happening. So you are standing in a bus. The bus goes forward. Your legs go along with the bus. But your upper body will say, I will not move. Your upper body will say, no, I will not move. So upper body is there itself. Your legs go forward. That means you are falling back. Got it? That's what is happening. And you can say finally the point, you can write one point. Hence, when an object or when bus accelerates all of a sudden, we fall back. We fall backward. Clear? Understood? Yes? That's good. So that is what static inertia or inertia of rest will mean. There are many examples that happen in our everyday life. One example we discussed, one very important example. Then other examples also, other cases also. Look at this. It's a very simple one, you can try at home also. Many of you would have tried. We have taken a glass and it has water. And on that we have placed a cardboard, and on the cardboard we have placed a coin. 1 rupee coin or 2 rupee coin or 5 rupee coin, any coin. Okay, now when we hit the card flies away but the coin falls down. That means coin is not moving along with the card. Coin is not moving along with the card, the coin is falling down. The question is why? The question is why? It's very simple. Again I am telling you, always go with two cases. Initial case, coin at rest. Coin at rest, it possesses which inertia? It possesses static inertia or inertia of rest. You can call it as static inertia or you can call it as inertia of rest. Then final case. Final case. The card flies away. The card flies away. Then you have to say, but the coin will remain there itself. Why does the coin remain there itself? The coin remains at rest. It will be there itself. It will be for a moment, it will be there itself. It will not move much. The coin remains at rest due to what? Due to inertia of rest or static inertia. That's it. Okay, done. That's it, your answer is done. You just have to mention, if you mention this point, the coin remains at rest due to static inertia, your answer is done. Actually, that is the most important point, this one. Okay, so now once you write this, after that you can say, after that because of gravity the coin falls down. So why is the coin not moving along with the cardboard or the card? Very simple, because of static inertia. it will remain there itself. Good? Wonderful. Okay, so this is another example. So we have many such examples. You can look at that. This is also a very good example. Okay, you try to understand why is this happening. We'll discuss that in the next class. Okay, because we don't have much time. We'll discuss that in the next class. Okay, so that's it everyone. That's it for today's class. Whatever is remaining, we'll discuss in the next class. So please understand inertia and Newton's first law of motion properly. They are very, very, very simple. Okay, thank you everyone. Thanks a lot.